So, yeah, thank you, everybody. I'll say, first of all, it's a pleasure to be there and to talk and expose what we do at Synchrotron SOLEIL regarding Python and even more. I'll show you. So as was introduced, I'm working at Synchrotron SOLEIL, so it's a large-scale facility. I will show what it is, and I will then turn to Debian packaging, because this is where our solution to fight against instability. So just an introduction. So the Synchrotron SOLEIL it's a large facility. We have a picture. It's on the left side, upper left side. You can see this is an aerial view of the site. There's a ring. It's an accelerator with electrons circulating inside it. We have magnets everywhere. And this ring is a little more than 350 meters, but the building itself is something like 500 meters circumference, okay? So around the ring, you have plenty of experiments. Each experiment, as shown on this view on the right side, it's a beamline, so we call it a beamline because there's a beam, which it is photons. The photon beam is something like a micrometer in size, so it's very tiny, and it's like a laser, I would say. And it then goes on an experimental station where you put samples, and you can study matter with this. So we study plenty of things: geology, archaeology, gases, solid-state physics, liquids, everything, biology. So plenty of applications. As shown on the screen, we have something like 60 million euros budget every year, and this money comes from the state. So this is public money. And in total, we have 29 beamlines. Each beamline may have different stations for samples, so different type of experiments. So it means we have a very large diversity of experiments running there. We welcome 4,000 visitors per year. They come on a proposal basis, so they propose experiments, and then we have beam time is given to them to perform experiments. So we produce a lot of data, and the resulting application of the data is to write papers, and these papers contribute to knowledge improvement. So we give knowledge to the community, the worldwide community. We are one of the synchrotrons on the world, and all synchrotrons contribute to the same task. To be more precise, on site, we have something like 100 scientists. So basically 2 or 3 scientists per beamline. And each scientist has its own history and habits. So they basically use plenty of software for treating the data. And we'll come back to this. But it means 100 people, crazy scientists, means complete diversity of anarchy of every point of view and different methodologies. So a very large diversity of solutions. And our group is there to support the beamline. So this is a large task. On the right side of the slide, you see there is kind of analysis of the requirements for the beamline. We have plenty of Python applications. More than half of the beamlines are using Python these days, but still we have strong solid rock, Igor and MATLAB still remaining, and a lot of Windows applications, because some of the beamlines are using dedicated spectrometers which come as a commercial product. 1/3 of the beamline are using GPUs massively to treat large data sets. Okay, so this is what we are. I show a detector, how it looks like. It's a box 30 centimeters wide, a big camera, kind of camera you can get, but it's 1,000 hertz, so it's very fast acquisition, and the pictures are large. But the resolution of the pictures is a micrometer, and we can even go down to nanometer scale. So we can have very tiny details in matter. And beamlines, they just collect the photons coming out of the ring, and then as they propagate through the beamline, different optics, focusing optics everywhere, just like optics, and then there is sample and detectors at the end. This is basically how it works. So we've heard about data deluge. for a long time. I'm sure all of you know that. But if you look back in time, you'll see that this has ever been there. In fact, the first notice of data deluge or information invasion or things like that dates from the 60s. And so it's been there forever. And in fact, computing has been growing like that forever. So at every time in history with computers, people have been talking about data deluge. So in fact, the conclusion is that there's no data deluge because technology evolves with the accumulation of data. And even though we produce more data, in fact, technology just follows. And we have faster computers, larger storages, faster networks. And all this allows us to handle the data. In our case, we produce something like 3 petabytes per year of data. This is quite something already. And we keep all the data since the origin. This is 2006. So it's been there for 20 years, basically. So we keep all this data available for the users and the community. So everything follows the Moore's law. There is a graphic on the right side that shows the evolution of the production of SOLEIL data, but also the dash curve indicates the worldwide production of data in exabytes. These are not gigabytes or terabytes. These are exabytes of data. And you can see that basically we follow the tendency. All right, so we make use of everything which is available, that is massive production of data, fast networks, GPUs, CPUs, multiprocessing, things like that. And we do have a lot of requirements for the analysis of all this data. So for me, there is no data deluge. This is my conclusion. A few ideas about, just to tell you what is data like. So we produce some vectors of data. So this is just points within one axis. We have images. We have also plenty of different types of images, either real space like a microscopy or in a transformed space. Depends how we measure. But basically, this is scientific data. These data are basically counts or things like that. They contain a physical quantity. And this analysis of the quantity, we extract information about the matter we have studied. So we have 1D data. We have 2D data. These are images. We have some 3D data. For instance, here, this is for solid-state physics. We have a gap, electronic gap in a material. So this is what we do. Also, we have tomography. So these are volumes. We just illuminate a volume. And from the radiographies, we reconstruct the volume. Each volume is something like 200 gigabytes. And this takes 1 second to measure. So every second, we have 200 gigabytes on the disk. And we also can combine everything to create hyperspectral data. This is 4D, 3D, 5D, 6D data sets. These can be massive. Now, our group is quite small. We are currently 6 of us. Was created 5 years ago. It's a groupe de réduction et d'analyse de données expérimentales à SOLEIL. And we try, with our limited staff, to cover plenty of services and support, including scientific software. Of course, we develop ourselves. We also distribute a lot of software, thousands of applications. And we deploy web services as well. So we're not very numerous in our group, but we do our best. It's a best effort initiative, and I think we do manage. We also maintain 3 central servers, and we have about 20 computer servers, heavy study computers on the beamlines, where they request massive data treatment, that is GPU and CPU, with a lot of memory. When I mean a lot of memory is a few terabytes of memory. Disk, we need a few hundred terabytes of disk. And we have, basically in one server, we have 10 or 15 GPUs per server. And each server has something like, I would say, 400 cores, things like that. And these hold in a 4U system, like on the picture. These are big machines, but we feed them with plenty of, as much as we can, in fact. We have some services. One of these is an immediate provisioning of virtual machines, which displays on the web. And this is what people use. They just log in with on a server, and using the browser, they have a display of a virtual machine which runs. They request something like 100 CPUs with a GPU, and they have plenty of memory, which is much larger than what they can hold on their own computer. And they have direct access to the data. This service is called Darts, and there's a web package. There's a package for Debian, which is called QEMU Web Desktop, that distributes that. If you install that, you will be able to provide this service immediately. So you distribute virtual machines. We have also a Jupyter Hub with Jupyter Lab in the background. And we have dedicated systems for computing material modeling. So this is dynamics of and structure of matter, or different type of experiments. The web links are in there, and the presentation is on the Discord page of the conference. So now let's come to the nightmare. We have hundreds of applications, thousands of libraries, and on our side, if we would support every installation of Python or anything else, we would spend our time having hundreds of people waiting at my door and waiting for solutions. Each of these would be different and specific. That is, it's impossible to handle the instability of current software zoology, I would say. So in my view, the complexity of computing is following also Moore's law, that is, it's exploding as well. And we are completely overwhelmed by the complexity of software and the instability which comes from the innovation, of course, but also this is part of anarchy, kind of. So every day we have questions. How to ensure the data analysis reproducibility? That is, you have a software and you want to give it to somebody else, and you say, it works on my side. Does it work on your side? It will say sometimes yes, but often no, it doesn't work because they have specific applications or other libraries that conflict. Also, you want to ensure stability of the software. That is, one time you maintain forever, or once you have installed it, you guarantee that it will work in a way which is stable for, let's say, a year or 2 years. But this never happens on a laptop. You change your environments every day. At some point, it breaks, and then you have to restart. You cannot do that on a server base. So this is not possible for thousands of users. How do you maintain the codes themselves for a long time? This requires a lot of bug reports and fixes and so on like that. So we are not enough on our side to do that. And how do you promote data sovereignty? That is, the data belongs to citizens in France, and this is the same for large-scale facilities. How do you make all this still controlled in terms of the data should not go abroad and disappear, and you don't know what is being done with it? So these are the main questions we have to face every day. So I have questions for you. Who is using all these Conda pips, things like that? I'm quite sure all of you will raise your hands. Yeah, okay. And okay, this is nice, thank you. But who has ever encountered unresolved dependencies? It is, how long does an environment remain stable, or how long do you have to rebuild your environment? That is, you install something, and after a few months, perhaps even a few weeks, it breaks because you modify things, and at some point you have to restart. So this, who has ever encountered conflicts? I'm sure also everybody that has been using all this, which are nice environments for installing Python libraries and more, I'm sure this is what everybody faces. And if you transport that to thousands of users, you understand that, first of all, it's not maintainable, and second, you cannot distribute a system for everybody to cope with all these problems. So you have to give something which is stable. And having a new tool for managing packages is not a good solution. There are many solutions for Python, but not only. For all the languages, you have package solutions for distribution and installation. None of them is perfect because it relies on instability. So in scientific computing, we are all happy to have a system. At least you buy a computer, you have a system running, you may change it, but at some point it runs. And scientists are just like the others. They like to have something that is stable. They rely on it. They know that if they click on Firefox, Firefox opens. If you click on this and you say, perhaps it will not open, then well, in the end, this is not satisfactory. So often for GUIs, there is no issue because GUIs are often isolated. So every isolated application you can distribute and it does not interact with the others. Even you can create environments. And in a way, if you don't touch it, the GUI will still display. But most of what we do relies on libraries, and we do that with Python, but not only, with Node.js or with Rust or with R. All of the languages have their own system, and Python is just an example. I call it an anarchy. It's quite provocative, but it's more like innovation, I would say. But as long as you get the habit to use a lot of libraries, then you expose yourself to a lot of the dependency nightmare. And this is difficult to handle. Okay, so how do you handle that? How do you maintain environments where you have a very large diversity? These are the questions we have to face. So just as an example, I take just a basic Linux environment, a basic machine with nothing, just a GNOME or Cinnamon or things like that, just a basic system. And we wish to install, well, the majority of software that most beamline will use, and that will, in a way, render the best support for the beamlines. And we want to use all the applications and all the libraries together. It's not one environment for one application and then another one, because you cannot merge these. So we have identified 54 main applications, and if you install that, you see that you have nearly 2,000 dependencies that come from this, and it creates 16 gigabytes of installation on the disk. So this is really massive. Of course, the 54 applications contain PyTorch and Jupyter Labs. This is not small packages. These are not small packages. But if we study the taxonomy of what packages are installed, we see that there are system libraries, which represent something like 35% or 36% here. We have Node.js and Python, which are about 30%. And the rest, which is our applications, are just 3%. So we install 3%, and all the rest is crap, I would say, or massive invasion on your system of all the rest. And all the rest, you understand, you have hundreds and thousands of pieces you don't even control. And every time there is one bug or anything that changes in one of these, in these so numerous dependencies, then your main application breaks. So this is an issue. So the pictures show basically the area of the squares indicates the proportion of the task. And you see the green square is quite small. So how do you package and how do you distribute? Of course, most of you will use Conda or something similar, and it relies on a community, of course, and most of you use Conda Forge because Anaconda is going commercial, so you have to pay these days for Anaconda. So people just install mini Conda and then they connect to Conda Forge. Conda Forge is anarchy, so you are never sure that the environment of some libraries that you install will not conflict with some other environments. So it is unstable by nature because you have thousands of developers, each of them change their code, and in the end, you have conflict loops that never solves. Also, Conda overloads some of the system commands, and this is also an issue because you see that your system is broken, but you don't know why. It comes from commands that just take over on top of the system. And last, environments cannot be merged together. If you have got an environment A and environment B with two nice libraries, you cannot often make A plus B, because often there will be library versions which will conflict, and then you cannot install. So a container, people talk about Dockers or obtainers. This is nice. It's supposed to run everywhere, but it is not as good as expected because these are static boxes. You cannot change them. And every time one of the packages changes, you have to rebuild everything. So also the task is on your own, and it requires a lot of maintenance. And at the same time, using GPUs for us is an issue because GPU do not, they still need connections with a host system, and then it's very difficult to use. And last, we use Linux packages, and we prefer that because you have, in a way, the guarantee that the system remains stable because everything has been done in this way. The counterpart is that the side effect is that you never have the last distribution of the libraries, but often it's not necessary. So our pragmatic solution for all this is to rely on a stable distribution. We have adopted Debian, and this way our software life cycle is well, it is limited in it expands on 2 years. This is a release cycle of Debian. So for at least 2 years, every 2 years, we make an upgrade of all our systems, and we have 2 years of stability. We also contribute to Debian. I will come to this. And we rely on the Debian Science, which contains, well, this is a richer environment of scientific libraries and software that exist on the Earth these days. And it is stable, because this is the forward of Debian is stability. So this is our solution. And this way, we can distribute systems which are stable. It doesn't prevent to use conda on the top. So Debian has been also adopted by CERN recently. And this is very nice for us, because this is a good sign that people think about stability is an issue, or instability is an issue, and there are solutions. So just to show you how does Debian works in terms of stability, we inject code, that is, we get source code on a Git somewhere, and there is a complete DevOps mechanism that ensures that everything, every step guarantees that the package is coherent with all the others, that is, the whole system does not conflict with it. And if there is a bug somewhere, it affects plenty of other software, but until it is resolved, well, you will work in order to resolve all the bugs so that everything works together. And the beauty of it is that it makes that the 60,000 packages in Debian that Ubuntu also uses, or Mint or MX Linux, all these distributions use the same core package of software. All of these are stable and can be used together. That is, you can install plenty of Python libraries together, and you are sure they work. There is no conflict. So this is nice, and we rely on that. So we are 2 developers at SOLEIL. There's myself and another guy in my group. And we also contribute to 40 kilo euros per year in subcontracting. And for this, we track all our contributions in a page, which the URL is shown here. But also you find it on the Debian servers as well, where you see the trace of everything we do. Up to now, we have pushed something like 400 new packages into Debian, and we maintain all of these. These are plenty of libraries, not only the main applications, but everything which is underneath. We've been pushing ourselves. We are at the origin of pushing JupyterLab in Debian, and this is nice. This represents 2 years of work. In total, on these 400 packages, just to tell you, there is about 100 which are Node.js for JupyterLab, and 70-something Python packages, which are mostly for science. But there's also for machine learning, for instance. So how do you contribute to Debian? It's not that complicated, but you have to follow a procedure where you have to create an account, and then you sign, you wave your hand for Debian developers, and you get advocated, so that they push you and they sign that you are something trustworthy person. And then at the end, you become a Debian maintainer, and after a few years, you become a Debian developer. And then it's not complex, but you have to hold for the procedure, and at the end, you will gain the pleasure to contribute something which is much larger than what you can do yourself. This is for the world. So that's it. Last one, about sovereignty. We at SOLEIL, the IT group has adopted commercial solutions, but on our side, we really push some sovereign solution. That is, we control everything. We have our servers, we install our systems, we have our own cloud for storing data. We distribute our own web services because this data belongs to all citizens in France. This is money for investing from the state. And we are extremely sensitive to the fact that everything that is put on the web somewhere on the cloud, external cloud, goes somewhere else, and you cannot keep the sovereignty of the data this way. So this is the data does not belong to you anymore. Okay, so I think I'm done, and I'm open to questions. Yep.
Thank you, thank you, Emmanuel. So we have time for some questions. If someone have questions, okay, there. Coming. It will be quick. Where it was there.
Thank you, great talk. Have you heard about NIX and NixOS? Because it seems like the declarative approach of defining your entire operating system seems like the end goal of what you are doing. So, yeah, what's your opinion on it?
So NIX and also GIX is similar. These are systems which allow indeed to reproduce an environment and with, well, you have a very high level of guarantee that the system will indeed behave as expected. And you can maintain different versions of everything at the same time. You can switch from one to the other. This is extremely mature system these days. On our side, NIX and GIX are not for servers, because managing all these transitions from one place to the other means that the users have to select a set of applications. For us, it's much easier to contribute to Debian, and even when it's in Debian, it stabilizes the software, which makes things simpler to create NIX packages or GIX packages. We have in our group, we have one of the GIX contributors, major, and then we also discuss of all this. So I know NixOS, but we rely on Debian because this is well known, and Ubuntu. So this way you touch millions of users. So our work then benefits to all these users, and I'm not sure there are millions of NixOS users. I'm sorry to say that. You have to face it.
Another question? Yes.
Thank you very much. So in practice, you install Debian-based Python libraries, and do the Beamline scientists accept that? Or is there a group that says, I need a bit more recent, I install my own Conda on top of that? What's the split there?
So what we do is we distribute stable systems, including all the libraries that the Beamline requests. If there's a missing library, we push it into Debian as much as possible. And once it's installed, we say this is a set which allows to use everything at the same time and with an extremely high level of confidence. But, as you say, sometimes somebody says, I want this version of the library, and I will come back to this. And then we say, OK, just use pip, for instance, or any other system, and we distribute pip as well. So they install their own environment. And then it's on their own. We say, you select that. You can do that. You can use Conda or whatever. But it's on your own. We won't do support for that, because there are so many different cases that it's not maintainable. Now, coming back to the different versions, often you import or you get a Git somewhere where there's a list or a long list of dependencies with labels for different versions, because you use a code which is not yours and which has, in fact, the Conda imposes to have, in a way, a list of libraries with versions to ensure that the environment can be reproduced. But then it will collide, because when you merge environment A with environment B, then libraries will get into conflict. So the solution for installation with different libraries only runs once. That is, you have a stable system, and somebody glues on the top a different version. But then you cannot merge all of this. The beauty of the systems, and we like them, is that the whole system is coherent. So we ensure first this, and then we let the users, we let the freedom for users to install everything else.
Okay, thank you. If there are some other questions, or maybe, oh yes, sorry. This will be the last one.
Thank you again. So I love your take on yes, everything you presented, but sadly I'm the only one using Linux in my company.
Yeah.
So I would like to know if you have any tips, or like what can you do to convince an employer or something to adhere of your vision.
So indeed, well, IT people, they like to transfer responsibility to somebody else. No offense, okay? So when they buy a system, they want to have somebody in charge of it, but not themselves. So they buy, they subcontract something, and for this, these are commercial products. It can only be like that. So you buy a service, you buy a system which comes with a service, and then they pay, right? So it's completely opposite to an open source system, whatever this is. So on the IT side, they want to have the stability of the system without anything running on it. I'm just summarizing. They want a minimalist system with, and the system only serves very simple tasks. That is a DNS, a proxy, a firewall, whatever. Okay, these are tasks which do not evolve in time. But on the opposite, you have scientists or developers, and they want innovation. They want innovation. And this you cannot do with IT systems, because these are completely opposite. They are stable for good reasons. But on the opposite, you need flexibility, but you also need stability. And our solution is to promote Debian. It doesn't mean that you cannot run Debian on a Windows machine. You just install WSL, and then you have it. Or you install a virtual machine, and you have it. So there's no blocking point. I would say if you trust your own data and you don't want the others to take over your own data, then turn to the right side of the open source and the free systems, because this way you control what happens to your data. Also for LLMs, we also have our own LLMs in SOLEIL, so that the data we put in does not go outside. We keep control of everything.
Okay,
yeah.
I'm sorry to interrupt, but yes, this was the last question. So let's thank our speaker again. Thank you so much.